Welcome back, everyone. Welcome back to Math Explore Infinity. Welcome back to the ultimate channel committed to propelling your understanding of mathematics to unprecedented heights and instilling unshakable confidence. While not everyone may be aware of it yet, I believe it is only a matter of time before this channel becomes the undisputed go-to destination, right, for anyone seeking a quantum leap in their mathematical comprehension. If you are watching this video and find yourself hesitating to hit that subscribe button, well, consider it your cue, right? I mean, take it as your signal. It's often when things feel a bit daunting that we need to take that leap of faith. I mean, it's actually when it feels scary to jump that you have to jump. So why not subscribe now? I mean, your mathematical journey is about to take off, and the only thing you will lose by subscribing, believe me, is the uncertainty in your mathematical understanding. So take the action and subscribe. As of the moment I'm recording this video, I mean, we have around 35 incredible mathematicians following the channel, which is quite amusing because I firmly believe there are more than 35 mathematicians out there. Of course, I understand that some people prefer to watch from the sideline without hitting the subscribe button, and that is completely fine, right? I mean, you have every right not to subscribe, but here is a favor I would ask, right? Let's not be selfish. As I used to say, what is the essence of doing mathematics if you cannot count on each other? Mathematics at its core is a collaborative endeavor, right? I mean, it's a shared language that unites minds and transcends boundaries. So if you are resonating with the knowledge and passion we are cultivating here on Math Explore Infinity, don't keep it to yourself. By sharing this video or promoting this channel, you are not just spreading knowledge, right? You are opening doors for those who might be grappling with mathematical challenges. So I invite you to take a moment, right? Be the catalyst for someone else's mathematical breakthrough, and let's build the network of, I would say, mathematicians, right, who support, inspire, and learn together. Subscribe, share, and let's amplify the beauty of mathematics across neighborhoods and beyond. So, having said that, let's start with, with our journey, right? In today's lecture, we are going to talk about the direct method of calculus of variation, right, which is a technique heavily used in optimization to establish the existence of minimizers. I mean, some of you may have heard about it already, right? If it's your first time to, hearing about it, all is right. I mean, one of the goals of this channel is also to break mathematics into pieces so that no matter your background, you can have a clear understanding of what is going on. So, in calculus of variation, the focus is actually often on finding minimizers of certain functionals, right? So let's consider a functional f, right? That operates on a subset U of a Banach space X, right? So this is capital X into R, right? And now say we are kind of, as I said, we're interested into, the minimum of the functional f, right, over X in U. Oops. So to properly actually account for the constraint that X must belong to U, right? U is actually, as I said, an open domain, an open subset of the Banach space X. So maybe I need to say that this space here is a Banach space. Right, and U is also open, right? It's open subset. So, as I was saying, to properly account for the constraint that X must belong to U, right? What we do, is that we extend the functional f to all of X, right? So we don't restrict ourselves to U, but what we do is that we extend this functional f to all of X in the following way. So we define the functional f bar defined from X into R bar. This is the 1 point compactification of R. So this is R union plus infinity. So we extend f actually to all of x by ensuring that any element outside of our subset U, right, is assigned the value plus infinity. So we define f bar from x to R bar the following way. So this is f bar of x is equal to, we write f of x, right, if x is in U, right, and plus infinity otherwise. Oops. Good. So this means that, as I said already, any point not adhering to the constraint contribute an infinite amount to the functional value. Of course, we also, we also extend the usual arithmetic on R to the 1 point compactification of R, right? So, in order to prevent issues that could arise from ambiguous operations involving infinity, right? For instance, subtracting or multiplying negative numbers with infinity are excluded, right? Just to maintain a kind of a well-defined structure, right? So, okay, so, oops, yeah. So, given this setting, probably I have to write it down. So, given this setting, right, it becomes clear that if there is any x, if there is any x in U, right, at all, probably should drop the at all, right? So if there is any x in U, right, that is, if U is non-empty, right, then a minimizer, say, we call it x bar, right, of f bar must necessarily lie in U, right, and coincide, of course, and coincide with a minimizer of f over U, right? So what I'm basically saying is that, after we extend our functional f, right, the mean of the functional f bar of the extended functional, right, is exactly the same as the mean of our original function f, right, over the set U. Okay, so throughout this lecture series, on non-smooth optimization, right, we will consider functionals of the form. Probably I have to write it down. Maybe no. So throughout this lecture series, we've considered functionals. So I think we write it down finally. So throughout this lecture series, right, we will consider, these are missing. We will consider functionals of the form f, right, defined from x into the 1 point compactification of R, right? I know usually people write bar to mean the 2-point compactification, but I mean here we only mean the 1-point compactification. And so maybe so we don't get lost. Oops. So this is the 1-point. Compactification. Okay, so now the set on which f is finite is called the effective domain. So those are some basic definitions. So the set of points, the set on which, I think it's better, the set on which f is finite is called the effective domain. So put it in color. So this is called the effective domain. And then I think it is usually denoted by so maybe I use it's called the effective domain. So this is wanted to use another color, but I think I'll stick with the same color. So this is a set of point x in x, right? Such that f of x is finite. So this is the effective domain of f. So we denote it by dom f. Okay, so another definition is that if domain of f, if the effective domain of f is non-empty, right? Then the functional f, right, is called proper, right? So a functional is said to be proper if if its effective domain is actually non-empty, right? People also say that, you might know it as saying, another way of saying that f is proper is that the inf of f, right, is finite, right? Means they are basically the same. Okay, so to establish the central existence result in the calculus of variations, we built upon the well-known Weierstrass theorem, right, which guarantees that every real-valued continuous function, right, on a closed and bounded set attains its minimum and maximum, right? This is what you know, right? If you don't know that, it's totally fine. So the Weierstrass theorem says that if you have a continuous function, right, a real-valued continuous function on the closed and bounded domain, then it attains its minimum and its maximum. But this actually holds whenever you are in finite dimensional setting, right? So, but the problem here in our case, in our situation, is that the problem here is that in infinite dimensional setting, right? In infinite dimensional setting, right? So maybe I need to write infinite. In infinite dimensional setting, we don't have any more, boundedness, right? And closeness. So bounded plus close does not imply any more compactness. So these two properties alone are not enough to, they do not, they are not equivalent, right? Because in finite dimensional setting, they are equivalent. So in finite dimensional setting, we don't have this anymore, right? So I mean, to convince yourself, you can actually think of, to convince yourself, you can think of, maybe, you can think of the closed unit ball, right? But in the space, say L2 of omega, right? Say the set of 1x, or the set of, say, your function f, right, in L2 of omega, right, such that the L2 norm of f is less or equal than 1, right? I mean, this is not, the closed unit ball in this space is not compact, right? This is what we saw when we discussed the race lemma, right, in my functional analysis lecture series. So I strongly invite you to have a look, right, at my lecture series on functional analysis. So we saw that the closed unit ball is compact, right? In the Banach space is compact if and only if the Banach space is, if and only if the Banach space is finite dimensional. So this is compact. I mean, if this ball would be compact, that would imply that the space L2 is finite dimensional, which is not the case actually. So this would be a good example to convince yourself that in infinite dimensional setting, boundedness and closeness, right, together do not imply compactness. So in order to extend, but we still want to, we still need this compactness properties, right? We somehow still want to have something similar, right? So in order to extend the Weierstrass theorem, right, to Banach spaces and functionals of the form here, what is that? And functionals of this form, right? We need to introduce some specific definition, right? So we need some specific definitions. The first thing is that since we are only interested in minimizers, right? So we only require one-sided continuity. So we write it down. So we put change the color. Since we are only interested in minimizers, we only require one-sided continuity. So the first point is we require one-sided continuity. I will explain what I mean by that. One-sided, it doesn't look nice. Sorry. Oops. One-sided continuity. Right, so this means, we are going to refine the notion of continuity, right, by focusing on lower semi-continuity. So this means we refine the notion of continuity by focusing on lower semi-continuity. Oops. I don't know, but somehow I always like to have something looks beautiful and so on. So we need one-sided continuity. So we refine ourselves to lower semi-continuity, right? To lower semi-continuity. And if you don't know what lower semi-continuity means, this is f is lower semi-continuous. So a function f is lower semi-continuous. in a point X, the space X, right? If how would I put it? If for every sequence, right, you should have a sequence xn, right, of element of x, right, such that xn converges to a point x, right? Oops. Then this implies that f of x is less or equal than the lim inf of f of xn, right? Of course, as n goes plus infinity. Okay, so analogously, I mean, you can define the weak and weak star lower semi-continuity, right, via weak and weak star convergence subsequence, sequences, right? I mean, what I mean is that, I mean, to define weak lower semi-continuity, you will need the sequence xn to converge weakly to x, right? And then the necessary part of this implication remains the same. Okay, so as I said earlier, the notion of compactness, so we will refine ourselves first to lower semi-continuity. And as I said earlier, the notion of compactness is more subtle, right, in finite dimensional spaces, right, because boundedness and closeness, do not anymore imply compactness. However, the notion of cohesivity, right, serves as an extension of the idea of boundedness in the context of infinite dimensional spaces. So the function f, is called cohesive, right? If put it in color, should have a sequence xn, right, of element of x, such that the norm of xn in the Banach space, the norm of the Banach space, the norm in how would I say that, the norm of xn, right, in x, right, so the norm that induces a topology on the Banach space x. So if the norm of xn goes to plus infinity, so then the image sequence also goes to plus infinity. So f is said to be cohesive, right, if it ensures that the value of the functionals, right, f of xn, increase without, the values of the functional f of xn, right, increase without bounds as the norm of the element in the sequence goes towards infinity. So this property actually serves, as I said already, as an analog of the boundedness property in finite dimensional spaces. So cohesivity actually guarantees that certain sequences cannot escape to infinity, right, without the functional values also diverging to infinity. So shortly speaking, cohesivity imposes a sort of a constraint on the growth of sequences, mirroring thereby the control provided by compactness in finite dimensional setting. So I said it once again, cohesivity, right? Cohesivity imposes a constraint on the growth of the sequence xn, right? And this actually mirrors the control that you have, right? The control that you have, the control provided by compactness in finite dimensional setting. So by utilizing the concept of cohesivity, one can establish properties in finite dimensional spaces, right? Compactness-like properties, in infinite dimensional spaces. So I'm with this refined definitions and properties. We can now prove the central existence result in the calculus of variation, right? In the calculus of variations, right? So, and the strategy of the proof is actually known as the direct method, as I said at the very introduction. Sorry. So now you have lower semi-continuity, and then you have coercivity. And then you claim that these two properties are enough to actually prove the central existence result in the calculus of variation. So theorem 2.1, which is actually the main theorem of this lecture. So theorem 2.1. Oops. This is the direct method. So probably I should just write direct method. Let me put it here. Okay, so what are the assumptions? So let X be a reflexive Banach space, right? So right, let me just highlight reflexive, which is important here. So X is a reflexive Banach space. Assume that F, we have our functional F defined from X into the one-point compactification of R satisfies the following. We have F is coercive, right? F is proper and coercive. Right? And F is also weakly lower semi-continuous. Semi-continuous. So then, in this case, the minimization problem, then the minimization problem minimize f of x, right, over x in x, let's call it p, right? So the minimization problem p, right, has a solution x bar in the domain of f. So again, let's go back to the theorem. So if x is a reflexive Banach space, right, and f, or a functional f, right, is proper, coercive, and weakly lower semi-continuous, then the minimization problem P has a solution. Of course, well, you might be wondering why here we assume that f is weakly lower semi-continuous and not lower semi-continuity. But what the thing is that, if you only assume, if you have only, if you only assume that f is coercive, proper, and lower semi-continuous in the strong topology, right, then it's actually difficult to verify, both properties for the strong topology. So this is one of the reasons why we kind of actually go for the weak topology, right? Because in the weak topology, it's actually easy to verify both that the function is coercivity of the functional and also the weak lower semi-continuity. So but don't worry. If you don't get it, but I think I will come back to this, right? I will come back to this when we talk about calculus of variation, right? I will tell you. We have a look at examples why we cannot actually fulfill coercivity and lower semi-continuity for the strong topology, and why we need to work with the weak topology. So we will come back to that. Okay, so under this assumption, properness, coercivity, weak lower semi-continuity in the reflexive Banach space, then you have existence of the solution of the minimization problem. So let's go into the proof. So proof. So the proof can be separated into 3 steps, right? So the proof can be separated into 3 steps. So the first step is maybe pick a minimizing sequence. I mean, this is the traditional approach, right? That I'm actually giving you. So first step, pick a minimizing sequence. So the first step is actually to pick a minimizing sequence. So how do we do that? Well, since f is proper, is assumed to be proper, right? There exists, an m, right? Such that m is equal to the im of f, right? Im of f of x over the x in x, m finite, right? Here, of course, I have to say that, I mean, although m equals to minus infinity is not excluded so far. Now, but now that you have that the existence of an m such that m is exactly equal to the infimum of f of x, right, over x in x. Now what we use is we use the characterization of the infimum. So by characterization, of the infimum, right, there exists a sequence, let's call it yn, right, in the range of f, right, in the range of f minus plus infinity, right? I mean, this is the range of f, right? So the range of f, I mean also the image of f, right? Shown. So there exists a sequence yn, right, in the range of f, right, such that yn actually converges to m, right? But because the yns are actually in the range of f, right? So this means that there exists a sequence xn, right, in x, such that yn, which is exactly f of xn, converges to m, right, which is the inf of the f of x. Oops. Right, and such a sequence xn is called minimizing sequence, right? So we put it here, such a sequence xn is called a minimizing sequence. And please always, observe that from the convergence of of f of xn, right, we cannot conclude about the convergence of xn yet. So the second step we do, let me just check the notation. So I use the Roman notation. So the second step is actually to prove that the sequence Xn contains a weakly convergent subsequence. So prove that Xn contains a weakly convergent subsequence. So this is the second step. Well, but actually to prove this, actually I claim that it is enough, right? So it is enough for us to prove that I claim that it is enough to prove that Xn is bounded. Right? I mean, do you agree with that actually? I mean, think of it for a moment, right? And probably put it in the comment, like why it is enough actually to prove that Xn is bounded. Well, this is for the simple reason that our space X, our Banach space X, is assumed to be a reflexive space. And then remember the Eberlein-Schmidt theorem. I mean, if you have knowledge of functional analysis, if you don't have, I mean, I strongly invite you to watch out. I mean, to take my lecture series, functional analysis, where we actually prove that if you have a reflexive Banach space, right, a reflexive Banach space, and then you have a bounded sequence in that reflexive Banach space, then you can always extract a weakly convergent subsequence. So this is why here it's actually enough for us to prove that Xn is bounded, because together with the fact that our space X is reflexive, we will be able to conclude that there exists a subsequence that converge weakly. So it's enough to prove that Xn is bounded. So for that, we proceed by contradiction. Suppose not. Suppose that Xn is not bounded, right? So this means that that is probably I write everything. That is Xn is unbounded, right? So this means that the norm of Xn it goes to plus infinity, right? As n goes to plus infinity. However, here comes the assumption on the coercivity of f, right? However, the coercivity of f then implies the coercivity of f then implies that f of xn actually goes to plus infinity as well, right? Which is a contradiction. Which is a contradiction to the fact that, I mean, in the first step you prove that, I mean, f of xn actually converges to m, right? Which is finite, right? By definition of the minimizing sequence. So hence, the sequence xn is bounded. Now, since we write it here, since the space X is reflexive, as I said, it follows from Eberlein-Schmidt theorem think there is something here. That there exists subsequence, let's call it x and k, right? Such that x and k converges weakly. I mean, this will be our notation for weak convergence, right? To x bar in x. So let me just highlight the Banach theorem. Again, please check out my lecture series on functional analysis, right? I mean, where I think I basically covered all the essential topics that you need to know, right? If you want to, to pursue advanced study mathematics, master degree or PhD. So, okay, so from the Banach theorem, we have the existence of a subsequence that converges weakly to an x bar, right, which is an element of x. And of course, this is actually our candidate for, this is our candidate for the minimizer. Okay, so the last step will be to show that this x bar is indeed a minimizer. So the third step to actually show that x bar is a minimizer. But this is rather straightforward, right? So, okay, so from the definition, from the definition of minimizing sequence, we also have, from the definition of minimizing sequence, we also have that, f of x and k converges to m, right, as k goes to plus infinity, right? Because the original sequence converges to m, so the subsequent will converge to the same thing, right? Because those are they are valued in R. Okay, so together with the weak lower semi-continuity of our functional f, right, we obtain, what we obtain is that f of x bar, right, is less or equal than the lim inf, right, of f of x and k, right? But this limit is exactly m, right? But on the other side, this f of x bar, because x bar is an element of x, it should be greater than the inf of f, right? So this, the inf of f, right, in x, which is m, should be less or equal to f of x, right? So this is, just to be precise, so this is by definition of the infimum, right? And this here, of course, is finite, right? This is what we saw. Okay, so you see that there is no room left for f of x bar, right? Apart from being the inf of f. So this means this. x bar is exactly in the domain of f, right? And the inf of f of x, right, over x in x is exactly f of x bar, right, which is of course greater than minus infinity. So it's not necessary. Okay, so hence, the inf is attained in x bar, right? So this is what we had to show. Okay, good. So you have proved the, central existence result of the minimization problem, right, of calculus of variation. So we use the fact that our space X was reflexive, right? But we can even, we don't have that space X to be reflexive, right? So if this is a nota bene, so if X is not reflexive, so if your Banach space X is not reflexive, right? So let me just highlight it's not reflexive, right? But X is actually the dual space of a separable space, but X is the dual space of Z, right? If Z separable Banach space, let me just highlight separable Banach space. So if X is actually the dual space, right, of a separable Banach space, then you can argue analogously, right, using the famous Banach-Alaoglu-Bourbaki theorem. And we can argue analogously, right, using the Banach-Alaoglu Bourbaki theorem. Again, I will not stop actually encouraging you to check out my lecture series on functional analysis. Again, we proved the Banach-Alaoglu-Bourbaki theorem in my lecture series, so please check it out, right? Functional analysis is kind of the bedrock, right, for mathematical analysis, right? So there's no way for you to run away of functional analysis if you are, if you want to do a master, a PhD, or if you want to delve into advanced mathematics, you need to know, you need to understand functional analysis. Well, why is this actually also important? Why is this actually true? If you replace X, right, by the dual space, right, of a separable Banach space, we can also do the same for the simple reason that, let me put it here, if Z is separable, right, the space Z is separable, then the closed unit ball, right, in X, which is equal to Z star, the dual space of Z, right? So the closed unit ball in the dual space of Z, right, is metrizable, right? Metrizable, of course, with respect to the weak star topology. Again, I went through the weak star topology, the weak topology in my lecture series on functional analysis, so check it out. Yeah. So if Z is separable, then the closed unit ball in the dual space, right, of Z is metrizable with respect to the weak star topology. By metrizable, we can actually construct a metric, right, that induces the weak star topology. So the closed unit ball is symmetrizable with respect to the weak star topology. So therefore, compactness, right? The compactness that we obtain from the Banach color glue. Therefore, compactness given by Banach color glue, because the Banach color glue Baki says that the closed unit ball in the Joule space is actually weak star compact. So the compactness property given by Banach color glue implies sequential compactness. So this will be the reason why if X is not separable, it's not reflexive, sorry, and rather is if X is not separable and rather the Joule space of a separable Banach space, then you can also, you can argue analogously, right, and prove the existence of a minimizer. Now let's have a lemma, right, that actually gives us some properties of weakly, lower semi-continuous functions. So this will be lemma 2.2. So let X and Y be Banach spaces, right? And again, we still have our functional f, right, defined from X into R bar. This is the 1-point compactification and not the 2-point compactification. You have f weakly lower semi-continuous, weakly lower semi-continuous. I've just write LSC, right, to say weakly lower semi-continuous. So if you have two Banach spaces X and Y, and then you have a weakly lower semi-continuous function f, right, then the following functionals are weakly lower semi-continuous as well. Then the following functionals put it in color maybe, are weakly lower semi-continuous as well. Notably, if you multiply your functional f by a positive constant, then the resulting functional is still weakly lower semi-continuous, right? If you add number 2, f plus g, right, for g being defined from X into R bar, weakly lower semi-continuous. So if you add two functions that are weakly lower semi-continuous, you still get the function that is weakly lower semi-continuous. This is kind of easy to see, right? So the third property is that, not the third property, but the third functional is that phi composed with f, right? For phi being defined from the point compactification of R into the point compactification of R, lower semi-continuous and increasing. So if you compose a lower semi-continuous, a weakly lower semi-continuous functional, right, with a functional that is lower semi-continuous and increasing, then what you get is a function that is weakly lower semi-continuous. And then the final function is that f composed with phi, capital phi, right, for phi defined from y to x, right, weakly continuous. Here we now say weakly continuous, right? Weak continuity here means that if you have a sequence yn that converges to y, then phi of yn, so maybe I need to drag it a bit today. Phi of yn converges to phi of y. So this would be the definition of a weak continuity. So f composed with phi, right, is also weakly lower semi-continuous, given that phi is weakly continuous, defined from y to x. And then if you consider the supremum of functional fi of x, right, I in I, with fi being defined from x into r bar, meaning to the point compactification, fi weakly lower semi-continuous, right, for an arbitrary index set I. So the fi needs to be weakly lower semi-continuous, and I is arbitrary. So this supremum is actually it's also, we need to get rid of this x here. Yep. So this supremum is actually, weakly lower semi-continuous as well, right, provided that all the fi are weakly lower semi-continuous. Okay, so and of course, note that what you need to observe is that property 5 doesn't hold, right? Does not hold. Oops. Doesn't hold for function fi, right, defined from x to r bar, right, data continuous. Okay, good. So now let's go into the proof. You're not going to do the proof, right, because it is quite easy, right? So I leave it to you, right? So of course, if you have any problem, feel free to drop it in the comment below, and then I'll be happy to assist you or to kind of provide some hint. Okay, so now we have an interesting corollary, right, that actually one of the direct consequences of the above lemma is that if you have a Banach space, so let X the Banach space, then this norm is proper, first of all, right? Since properness is clear, right? Because 0 is always less than plus infinity. It's coercive, right? Coercivity is also clear, so then the norm defined on X is proper, coercive, and weakly lower semi-continuous. Weakly lower semi-continuous. Okay, so the proof as well, I mean, it's not difficult, right? I mean, again, I invite you to try it out, right? So I think properness and cohesivity, I mean, they are quite clear, quite obvious, right? So the thing that we have to deal with is probably weak lower semi-continuity. But the hint I'm giving you, I mean, which basically gives you the result directly, is that the Banach space, right, X, the norm of X can be written as the supremum of the absolute value of X star comma X, right? This is the duality pairing, right? Over the X star in the dual space X, such that norm of X star is the operator norm. X star is less or equal than 1. Right? So this is the hint I'm giving you, and of course, remember what we proved, right? That the supremum of a family of functions that are weakly lower semi-continuous is weakly lower semi-continuous, right? And then here you have a function that is, I mean, you have linear functional, they are continuous, so they are even weakly lower semi-continuous. I mean, well, okay. So this will be the, I mean, the kind of the hint I'm giving you. So this is easy, right? I mean, if you don't see how this gives you the result, again, feel free to drop a comment and then I will reply. Okay, so a function that we will deal with frequently in this lecture series is actually the indicator function. I'm going to define it, so this is different from what you know. So the indicator function of a set U, right, subset U of X, right, is defined as, just highlight indicator function. So this is defined as delta U of X, right? So this is, so this is 0, right, if X is new, right, and plus infinity if X is not new. So this is how we define the indicator function, right, which is kind of different from what you know from the characteristic function, right, that takes value 1 and 0. So this is the indicator function. Okay, so the purpose of this definition is, of course, actually to reduce the minimization of a functional f, right? The purpose of this, probably I write it somewhere. So the purpose of this definition is, of course, to reduce, put it in color, to reduce the minimization functional, to reduce the minimization of a functional f, right, over the x in U, right, to the minimization of a functional f bar, to the minimization to the minimization of f bar, right, which I define now to be f plus delta U, right, over x. Right, so basically what I'm saying is that the mean of f of x, right, over the x in U is exactly the mean of f bar of x, right, over x in x, right. because observe that, f bar of x actually takes the value plus infinity if x is not in U, right? So in that case, anything is a minimizer. But if x is in U, then the minimization, those two minimization problems actually coincide, right? So I think it is rather clear, right? Okay, because of the way we define delta U, right? Which is plus infinity if x is not in U, and 0 if x is actually an element of U. Okay, so the following result, right, is therefore important for showing the existence of a minimizer. So this is lemma 2.4. So let X be a Banach space, right? And U is actually a subset of X, right? Then the indicator function delta U is number 1. The indicator function is proper, right? If U is non-empty, right? I think this is rather clear. The inf of delta U of X will be finite if only if U is not empty. So the second property is that delta U is weakly lower semi-continuous, right? If U is convex and close, right? And the final property is property 3. Delta U is coercive if U is bounded. Okay, so for the proof, so let's have a look at the proof. I think the first one is okay, right? Delta U is proper if U is non-empty. I think this is okay, right? So check it yourself, right? It's actually rather straightforward. So the second property says that delta U is weakly lower semi-continuous if only if U is convex and closed. So this is what we are going to prove. So assume U is convex and closed. So we want to show that delta U is weakly lower semi-continuous. So we pick a sequence. So let Xn be a sequence in X such that Xn converges weakly to X. Right? Now you have two possibilities, right? So if X is in U, then we have that delta U of X, right, is 0. This is by definition of delta U. And this is of course less or equal than the lim inf of delta U of Xn, right? Because delta U of Xn can take the value 0 or plus infinity, right? So this means we have weak lower semi-continuity. So this is weak lower semi-continuity, right? This is in the case where X is actually in U. Now, if X is not in U, right? So maybe I say let X not being an element of U, right? Since U is convex, this is why we use the assumption, really. Since U is convex and closed, U is weakly closed. Again, you see this is just a result of functional analysis, and then again, I went through that in my lecture series on functional analysis. We saw that if you have a convex set, then closeness and, strongly closed is equivalent to weakly closed, the convex set. So since U is convex and closed, then U is weakly closed, right? Because for convex set, strong closeness is equivalent to weak closeness. Maybe I will write it here for strong. But please check out my lecture series on functional analysis. So for convex sets, strongly closed, or just close, right? Equivalent to weakly close. So since X is not in U, and that U is weakly close, then this means there are some terms of the sequence, there's a rank such that which the terms of the sequence are not in U anymore. So this means, no, just say rather, there exist, there must be, this is the right thing to say, there must be an N, the rank, starting from which the term of the sequence xn, right, are not in U anymore, right? Otherwise, if this is not the case, otherwise we could construct, a sequence with xn actually converging to x in U, right? Which is obviously in contradiction to their function, right? Let's say in contradiction to the assumption, that x is not in U, to be more precise. So because there are terms of the sequence such that xn is not in U, thus delta U of xn, right, is equal plus infinity, right, for every n greater or equal than n, right? Hence delta U of x, right, which is equal to infinity, of course, is, I want to write less or equal, but this is even equal, right, to the lim inf, maybe drag it a bit to the left, the lim inf of delta U of xn, right, because all these things in the limit, this is plus infinity, right, so that's why I'm saying it is quantity. So this means, once, just write once delta U is weakly lower semi-continuous. Okay, so now the last property we have to prove, this is 3. We want to show that delta U is coercive, right, if U is bounded. So assume U is bounded. So this means that, U is contained into a ball, right? I'll just write for some R positive, right? If you're confused, this is just another way of saying that this is the ball centered at 0 and radius R. Okay, now let me just recall what we want to show. We want to show that we want to show that delta u is cohesive. Okay, so for that, let xn be a sequence in X, right? If the norm of xn, probably I will just, if the norm of xn goes to plus infinity, right? Then there exists a rank starting at which all the terms of the sequence, in norm, are greater than r, right, for every n greater or equal than n. And thus, xn, right, they are not actually part of the ball of radius r centered at 0, right? For every n greater or equal than n, right? Because for every n greater or equal than n, the norm of xn is strictly greater than r. So they cannot be in the ball, the ball of radius of centered at 0 and radius r. So from this, we can conclude that hence, so because you're not in the ball of radius r, they cannot be in u because u is actually contained into the ball. So because of this, we can conclude that delta u of xn, it's even plus infinity, but we just like goes to plus infinity as well. Once delta u is cohesive. So this ends the proof and also ends this lecture on the direct method of calculus of variation. So I hope you enjoy it, and again, check out my lecture series on functional analysis. And well, until then, stay safe and keep exploring, keep learning, keep watching my videos. And of course, if you have any problem, feel free to contact me. And yeah, I'll be happy to help you, to assist you with your mathematical issues, or if things that you, with your career, so to speak. Okay, so thank you once again, and see you in the next video.